In this video, I'll pick up where we left off last week, where we started the chapter on congruence and similarity by transformations. And remember, transformation is just a term which refers to all sorts of isometries, including translations, aka moving an object. Like we looked at a few translations, like for example, say we were to take a trapezoid and move it up 4 units and to the left 3 units or something. The various ways that we write transformations, including what we call a slide arrow. We also talked about rotations, and remember the key there is it's all about the center. It's about keeping it the same length and the same angle of rotation with regards to the center. So, the key way to perform a rotation is to connect each point of your figure to the center and then rotate that particular line segment by the angle. Like in this case, we took C, connected it to the center, and then rotated by 90 degrees, and that line ended up over here, which kind of which told us, well, where will the point on the congruent triangle end up, as well as how lines are similar with regards to rotations and translations. One other thing I wanted to mention about the online homework, just in case any of you guys were stuck on this type of question. But it said something like find the image of a line under transformation. Well, you could take an equation and plug in a transformation into it algebraically. But another way to do that is just, well, if you have an equation of a line, we can find points on the line and apply the same sort of procedures that we were working on in class to do that. Also, I wanted to be mentioned to be careful on the online homework, because sometimes it will ask you a question a little differently. Instead of asking you to find the image, it'll give you the image and ask you for the original. It's sort of like if we have, the new image, we want to figure out, well, where was it originally, by basically reversing the transformation. But anyways, we were talking about reflections as we wrapped up, and we looked at an example about reflecting a triangle about a line L. And I also wanted to mention that one of the online homework problems was not the correct image under a reflection. Remember, the key with a reflection is that each point needs to be perpendicular and equidistant to the line of reflection to its image. So, like for example, looking at this particular triangle and its image after it was reflected across this particular line L, the thing that we want to do is draw a perpendicular line from each vertex to the line of reflection itself, and then mirror that by basically just duplicating it on the exact opposite side. So with B, we want to reflect it over here, so we take the same distance over this way, and this would give us the location of its image. And the same thing for C and A, and that would give us this figure. And again, to help visualize reflection, I think it's helpful to orient your line of reflection vertically, so that way we can see that it is properly mirrored. Anyways, let's do another example, and it's also quite a bit easier using the Cartesian coordinate system, because you can't even use the coordinates as well. But the first example says to reflect the given, and this is in our notes from last week, which you can also find on this Canvas module if you lost track of it. But it says to reflect the given trapezoid about the x-axis. So first of all, let's take that same mindset and figure out how to do it. But basically, we have the x-axis is the horizontal line, which is passing through the origin. But basically, we'd want to make sure the great thing about the XY, Cartesian coordinate system is that it is rectangular, meaning that everything is perpendicular already. So if I want to make sure that this is reflected across this axis, basically I just follow along the grid lines, because this grid line is perpendicular to the x-axis. So it makes it very easy to say, okay, well, this point is 1 down, so this point should be 1 up. And also notice that the x location will stay the same. So if you're thinking about it based on the coordinates of this trapezoid, like this one is -1, -1, this one is 3, -1, it would keep the same exact x component. The only thing that would change would be the y component. So A prime would have the coordinates -1, +1 instead. And, same for the other point. Well, B would reflect across the x-axis and just end right up here. And it would change to a positive value in the y value. So this would be 3, 1 for B B apostrophe. And the other two, this was -2, -3, so this would become -2, +3, of course, or you just count the same distance across. And of course, you kind of visualize what this looks like. Again, we could use a ruler and so forth to be a little more exact, but since I'm doing this on my computer, much harder to use a ruler and a compass in this particular case. But anyways, we would get the image of the trapezoid under the reflection about the x-axis. And similarly for the y-axis, instead of flipping the signs on the y values, you'd flip the signs on the x values. And this kind of gives a little bit of a hint about how would we do this algebraically. But basically, you could perform such reflections by changing your equation by replacing them with either -x or -y. So say, for example, you had an equation of a line, and you wanted to know what would this equation be if it were reflected by the x or the y-axis. Essentially, it would just be a matter of changing one of those to a negative, and I'll let you think about which will be which just based on this example. But additionally, a glide reflection is just a reflection who has been done after performing a translation first. So essentially, move it, then reflect it. So like looking at the second example, it says on the second graph, perform a glide reflection by the transformation 5 to the left and 2 up, and then reflect about the y-axis. So let's first perform the translation, which would be basically be taking each of these points 5 to the left. So starting with the bottom left point of the trapezoid, moving that 5 to the left, it would end up right over here. And that would leave this point right here, point A. And let's go ahead and finish labeling them because A, B, C, D. And then point C, if we move this 5 to the left, it would end up 1 to the left of the y-axis, and that would have to leave that other point there based on the symmetry of this isosceles trapezoid. But anyways, there we would have first so that would just be a translation. So a glide reflection would mean first moving it, then performing a reflection. And now it says to reflect it about the y-axis afterwards. So again, algebraically, we could change this equation by inserting those algebraically into, again, if it had an equation, but it's a trapezoid. Just like an equation can be translated using algebra. But anyways, if we reflect this across the y-axis, that means that this is going to be our line of symmetry, and it will end up over here afterwards. And again, if we take some of those new points, this would be the point -1, -2, -1. That would change only the x value, and the y value would stay the same. So that would be +2, -1. And then, this point is 1, 2, 3, 4, 5, 6, -6, -1. That would become +6, -1. So that would be a little bit off the page. And anyways, we could, again, use symmetry to get the rest of those points. But I think you get the idea when it comes to a Cartesian coordinate system and reflecting across the x and the y axes. It's just a matter of changing the signs on the correct point. And I think one of the homework questions asks you to reflect it about the line y is equal to x. And what I wanted to mention about that is all you have to do there is change the values of your x and y, because that would, similarly to this example over here, this would be a 45-degree reflection, and basically you're reversing the roles of what x and y would do. So say, for example, 3, -1, that would become -1, 3, because they're equal. And if you draw the line, you'll kind of, if you draw the line y is equal to x, you'll kind of see why. Anyways, in the next video, we'll talk more about dilations and then follow that up by talking about tessellations of the plane.